Hello and welcome to the UFS webinar. This webinar is hosted by the National Weather Service Office of Science and Technology Integration. The goal of this webinar series is to enhance communication and share advancements in all aspects of the UFS, in both research and operational settings. I am Stacy McKell, and I'm here to coordinate and deliver the webinar. Feel free to contact us at OSTI if you have any comments or suggestions. Also, if you have any recommendations for speakers that you would like to present at this webinar, you can email us your recommendations to ufs.modeling@noaa.gov. Again, that's ufs.modeling@noaa.gov. We'll take your suggestions into consideration. So due to the high number of attendees, you'll be in listen-only mode during the event. You will not be able to unmute. If you have any questions now or during the event, please submit them on the Google document that will be provided in the chat box. Presentations last about 45 minutes, followed by questions and answers for 15 minutes. Type your questions on the Google document during the presentation. That Google document will appear in the chat box. Today's presentation is Enhancing Forecast Value with Artificial Intelligence, and our presenter is Sue-Ellen Haupt. So Dr. Sue-Ellen Haupt is a senior scientist at the National Center for Atmospheric Research, also known as NCAR, and Deputy Director of its Research Applications Laboratory, RAL. She's also a Fellow of the American Meteorological Society, where she currently serves as Commissioner of the Commission on the Weather, Water, and Climate Enterprise, as well as contributing to founding directors of the World Emergency and Meteorological Council. Dr. Haupt is an expert in boundary layer meteorology, large-scale atmospheric dynamics, applications of artificial intelligence, and in the environmental sciences, renewable energy, dynamical systems, numerical methods, and computational fluid dynamics. Her specialty is in applying novel numerical techniques to problems in the environmental sciences in both basic and applied research. I will turn this over to Dr. Haupt so that she can begin her presentation. Thank you very much for joining us.
Okay, thank you, Stacy. Let's see, I need to share my screen. Can you enable that, please?
Yes, just one moment. Okay, let's go. 1 second, please.
Okay, are you seeing my presentation now?
I do see it, yes.
Okay, wonderful. I'll be talking about the value that we can add to our forecasts with artificial intelligence today. And I'll plan to talk about first, why do we want to do this? Who's been doing this? Who's been advancing AI? Then talking about a systems approach that includes blending the numerical weather prediction with AI machine learning. And giving example for renewable energy, then talking about using AI/ML for severe weather forecasting, model parameterization, dynamics, and downscaling, and finish up with where are we going? How can we best leverage AI machine learning? So I've been doing artificial intelligence applications for quite some time. First seminar I ever gave on it was probably the first one given at NCAR, and that was in 1996. It was a CGD research report when I was a young research scientist, and it was entitled Eigenvalue Matching, a Traveling Salesman and a Genetic Algorithm. Well, what is a genetic algorithm? You'll hear words like evolution, population size, natural selection, having parents, offspring, mating, mutation. Of course, you have a cost function because it's an optimization problem. And you're able to do things like, given data on where contaminants might be, measurements from the field, estimate what the actual wind direction might be by having a dispersion plume model. So that's the type of work I started on. Published a book with my husband on practical genetic algorithms in the late 1990s. First and second edition came out later. And then about 10 years later, worked with the AI committee of the American Meteorological Society to codify some of our workshops and lectures into a book, Artificial Intelligence Methods in the Environmental Sciences. Now, we have a long history of working through the American Meteorological Society to advance the use of machine learning in environmental sciences. We have a great cadre of past chairs who recently got together to write a book, write a BAMS paper on the history and practice of AI in the environmental sciences. And as part of that, Philippe Tissot took some leadership on estimating over the last 20 odd years, how many papers have we had in our AI conferences at AMS? Well, first you'll notice that we started out with biannual conferences, only 2 years, and then started having annual conferences in around 2013. But those early years, there was a lot of interest early, but then you can tell there was an AI winter that came through in the early mid-2000s, a second one in the mid-10s, but then since about 2017, the number of papers being submitted is really on the upswing, with the exception of 2021, which was really the full pandemic year. But this past year, 2022, 179 papers at the AMS meeting. Now, what types of techniques have been used? Well, we see the gray here is neural networks have been pretty prevalent throughout. Early on, you had a lot of more heuristic methods like fuzzy logic that you'll find less prevalent now. We had support vector machines became popular for a while. You'll see the genetic algorithms here in the dark blue. Some of that were my students. Then tree-based methods have been around most of the time as well. But recently, what's really caused the resurgence that we've seen in this uptick is deep learning. And that's what we've heard a lot about in the media and where some of the most forefront applications are coming from. So what is, when we think about weather forecasting, we often think about our numerical weather prediction models. And they're based on the Navier-Stokes equations, where we discretize the PDEs that we have there. We add physics parameterizations, bring in data, pre-processing, post-processing. But then the second method is very empirically based, beginning with data, finding patterns. That's where artificial intelligence comes in, beginning from what we used to call statistical learning, statistical methods, but have evolved into a lot more methods that allow nonlinearity as well. Now, I claim that the best approach might be just combining the best of both of these methods. When we think about using AI for weather forecasting, where can it come in? Well, the holy grail is a machine learning dynamical core. We're not there yet, but I'll show you in a little bit some of the first steps that are being taken in that direction. A little more possible are the machine learning parameterizations. Here at NCAR, we've been involved with some of that, and I'll talk a bit more about those. But the low-hanging fruit is really post-processing what we've done with the physics-based NWP models. And we'll talk a little bit more about that now. So this low-hanging fruit has been ongoing for a long time. Of course, everybody's aware of some of the statistical work that's been done, and Bob Glahn started some of that, quite some time ago. But now we can use machine learning as well. And at NCAR in the late 90s, they began developing dynamic integrated forecast system, basically a blender that brings together output from multiple models, brings in observations, and optimizes forecasts. So the idea is it creates predictive relationships between the model output, the observations, and the variables you wish to forecast. So it optimizes that. And it enables decision support. It uses real-time data, so very much an Internet of Things application, and it uses large amounts of data, big data application as well. We need data both in real time to initialize the forecast, as well as historical both model and observational data for the training. So, Diecast was originally developed for the weather channels. They started going international with their forecasts. They realized they couldn't do it with human forecasters alone anymore. So they came to NCAR in the research application program. I wasn't there yet, but the great scientists and software engineers who were there then began this. Now it's used in a lot of other projects as the weather engine. Things like optimizing predictions for surface transportation, for solar energy prediction. We'll talk more about that in a minute. Wind energy, precision agriculture, and commercial forecasting companies that have used it along the way as well. So what is Diecast? Okay, we begin with data from various models. You'll notice that some of these are NOAA models, able to get the free output. This image was made back when it was GFS instead of UFS, but you can pretty much just, at this point, of course, we're using UFS. Other model output, bring in whatever we want, Canadian model, ECMWF, whatever. These days, we're also including machine learning models. We then post-process to bias correct each of these independently, and then use data from measurements to optimize and integrate post-processes so that we can get out multiple weather variables. Now, typically when we apply Diecast, if we look at the root mean square error versus lead time, this is out to 72 hours. All the colors are the bias corrected input models. The Diecast by design will have, on average, the lowest RMSE. And in the case of things like wind speed, we often find it beats the best model by on the order of 10 to 15%. So it makes it worth doing something like this to correct output. Now, we've been improving it gradually over the years. That's kind of the basic. Some more recent improvements for probability of Precip using machine learning. Again, this is a Breyer score where we see that the bias corrected, and again, this was GFS rather than UFS, but similar results, and the gradient boosted model in this case that goes into Diecast is even better on lead times out to 9 days. Looking at shorter lead times out to 120 hours, you'll see very similarly the gradient boosted methods can do better. The other thing we've been doing to update it is clustering climatologically similar METAR sites and coming up with 8 different clusters that are used then for training the model. Now, in the research applications lab at NCAR, we do a lot of applied projects, and I myself have been leading multiple renewable energy projects, most of which use AI as part of them. And one of the first big renewable energy projects we had was with Excel Energy in Colorado. Also has sites in the Midwest as well as Texas, New Mexico, etc. And you'll see the system we built for them. Of course, we have data that comes in from the centers. We had a very customized version of the weather research and forecasting model, ensemble versions of models, but we also have input of multiple data. Right at the center is Diecast, but we also have several other AI methods. For instance, solar energy nowcast system, extreme weather events, an expert system to try to leverage data upstream of the wind farm, power conversion using machine learning. The end user, in this case the utility, cares more about the power than about wind speed or global horizontal radiance. We do data mining for load estimation and use analog ensembles for probabilistic information forecasting. And what Excel Energy found is that they began their project with us in around 2008, and their original typical mean absolute error was around 17%. By the time we delivered the full system in 2014, it was down to 10%. That's a 40% improvement, but more importantly, they calculated that it saved their ratepayers roughly $60 million over that period by calculating on day-ahead forecasts alone. They also found that it saved more than 267,000 tons of CO2. So that's a real emission savings that can be done by optimizing the use of their clean, renewable energy. Now, we were so successful with wind and Excel that we moved to solar power forecasting in a project funded by the Department of Energy. And you can see the huge difference between a clear day, in this case, the global horizontal irradiance, the weather variables in red, the power is in blue. Compare that to a cloudy day. That means that we have to be able to predict clouds and aerosols. That can get harder. We developed a full system that we call Sun Forecast to do that. And much like we did in our other system, we combined the best of numerical weather prediction with artificial intelligence. In the day-ahead system, by day-ahead, they care about 12 to 36 hours. They're making predictions in the morning for the following day. Then we blend the information with Diecast. But they also have to make split moment changes as changes happen in the grid or the weather. So we also provide a nowcast system that is the first 6 hours prediction every 15 minutes. And again, you'll see that in red, we have various AI methods, integrating, using special information like total sky imaging. We bring in satellite data that goes into a statistical forecasting method, as well as a method that was developed by Colorado State University. We then have to blend, so we have a seamless prediction in time. Again, convert to power, and we choose to use an analog ensemble so that we can provide a probabilistic power estimate. Now, what are some of these specialized AI methods? We talked about Diecast a little bit, but let's talk about StatCast, the first 6 hour forecast engine. During this project, I had a really great graduate student from Penn State working with me, Tyler McCandless, and he and I looked at this and said, there's different regimes where the behavior is different. For instance, the green line here plots the top of the atmosphere global horizontal irradiance. What we really care about, we can calculate what that's going to be on any particular day and hour. But we, on a clear day, and this is, a year's worth of data from NREL in Golden, Colorado, we have some attenuation by water vapor, aerosol, etc., even at high altitude. On a partly cloudy day in Colorado, we tend to have clouds come up in the afternoon, so it's attenuated a little bit more. And then on one of our few cloudy days, totally cloudy days, not nearly as much GHI reaches the ground. So Tyler said, well, what if we divide into different regimes? And he designed this process where, our base case is, what if we take all the data from, at least a year's worth of data, we actually had more, and build one artificial neural network using all that data. We actually want to predict clearness index, which is the actual GHI that hits the ground divided by that top of atmosphere. That way we take out, trying to predict, we don't include solar angles and changes in solar angles. Our baseline is persisting that clearness index. So it's just a persistence baseline. But then the regime-dependent method used k-means clustering to first break it into regimes, the data into regimes, then apply the artificial neural networks independently to each regime so that we got another clearness index prediction. When he did that clustering, we ended up with some very distinct regimes that we could identify on what was happening, whether there were changes happening in phase space, and it kind of made sense. And then when he did the calculation and looked at improvement over the persistence base case, we found that using all the data, there was about a 14% improvement, but using the regime-dependent method, almost 19%. So it was worth breaking it into regimes. Now, I've mentioned the Analog Ensemble a couple of times, and I'm sure many of you have heard of it. Developed at NCAR, first by Luca Della Monica, now being used also by Stefano Alessandrini. And what it does is it looks at today's forecast for tomorrow, or whatever your lead time is. So it looks at the forecast, then it looks back over the historical data for the most similar or analogous forecasts. It chooses, 20, 30, whatever you choose, and that becomes your PDF. The mean, that's your ensemble. So the mean of that ensemble becomes your improved forecast, and because you have a PDF, you're able to quantify the uncertainty bands. Now, they've done a lot of research on this and find that it tends to be as reliable as some of the best ensembles in the world. Now, when they apply it, in this case, here we're looking at bias on global horizontal irradiance by lead time out to 44 hours. So it's a little more than a day ahead. Worst solar originally is the black lines with, the uncertainty bars in them. And you see that the analog ensemble, either with or without an additional bias correction, is a lot better on eliminating that bias. When we look at, applying it, in this case, for instance, the observations are the black line. The Diecast result, which is already optimized, is the red line, but the yellow dashed mean of the analog ensemble is yet better. But because you have that information, we're able to also plot flow-dependent uncertainty bars. And that has been very successful, and we're using it in our systems now. Our most recent application has been working with the Kuwait Institute for Scientific Research to build a full wind and solar power forecasting. The diagram is shown here. Again, we're bringing in physics models, global models, including UFS now, Canadian GEM. We're working to integrate ECMWF now. We run our own WRF solar wind optimized for the renewable energy variables, as well as some specialized versions of WRF that do local data assimilation. But then we have a lot of artificial intelligence methods, again, with Diecast as the centerpiece. Here we're using Analog Ensemble to do that power conversion on top of Diecast, as well as to quantify the uncertainty. But then the sponsor wants us to add the total for wind and solar, and of course we can't just add probability bounds, so we use a shocky shuffle approach to combine those probabilities. Again, looking at a few of the systems and how they're working. StatCast Wind, okay, the near-term wind forecasting system. If you look at the first 6 hours here compared to the orange persistent lines, all our artificial intelligence methods are beating that. A little hard to tell if the AI methods that we tried, based on neural nets, really are beating Diecast or not. So blowing it up here over the 15-minute to 60-minute time period, again, beating persistence even in the very short term. And Diecast is the gray line, starts out beating Diecast, but crosses over. At this point, Diecast is doing pretty good. So we just left Diecast in the system. Now on the solar side, we used a model regression tree and some software called Cubist to do the short range forecast. Here you see persistence is the red line that goes off the chart pretty quickly in terms of error. We're comparing, can we do better than Diecast in this very short term? And for solar, the Cubist algorithm does do better for the entire period. And in fact, the plot on the right plots the percent improvement over Diecast, beginning with almost 50% and then evening out to about a 10% improvement. So we do use that in the full system. How's Diecast doing itself? Well, here we're plotting, the input. Here, the Canadian model, again, this is a root mean square error. For wind, GFS, now UFS, is in yellow. Our WRF solar wind is the gray, which only goes out to a couple days. But then Diecast is improving on all of those for both wind on the left and solar on the right. And as you saw, for the first 6 hours, the nowcast systems are even better. The Analog Ensemble, can it again improve on Diecast? And a little, the answer is yes, by a little, but we can also use it to directly do that power conversion. And it is an improvement in all seasons of the year. Now, then, as I mentioned, we combine the wind and solar into a single forecast, apply a shocky shuffle, which is basically a reordering of dates, that we apply in times, and then are able to come up with a blended probability band. And you can see this paper by Stefano Alessandrini and Tyler McCandless on how they do that if you want more detail. Okay, so that was renewable energy. That's not the only way one can use AI. Severe weather as well. And one thing we've been working here at NCAR on is building models for fires, wildland fires, where we actually have the fire interacting with the NWP model, basically a WRF version model. But one of the real causes of error and uncertainty is bad fuel moisture estimates. basically they only go out occasionally and measure fuel moisture. But can we use real-time data to try to get a more dynamic estimate of this important variable? And the data that we're going to use is basically WRF hydro, which gives you things like evapotranspiration, land use category, soil moisture, etc. Bring in satellite data. This was on a NASA project led by Branko Kosovic. A lot of the machine learning was done by Tyler McCandless. Look at the surface characteristics and then train to the periodic observations of fuel moisture content using machine learning. So Tyler applied several different methods, and came up with ways to do that dynamic estimate for both dead fuel moisture and live fuel moisture, so that we were creating a gridded product of both of those that was updated on a daily basis using all that real-time information. What difference does it make in actually modeling? Well, a case study was done on the Cold Spring Fire in Colorado, and looking at differences in dead fuel moisture. Here, looking at the constant dead fuel moisture, the model footprint for the fire is the orange. Very different, much larger footprint for the machine learning based dead fuel moisture content. You can see here on the right, we have much more information, more granular information with the machine learning model. Now, you do compare it to the actual footprint of the fire and you say, well, you got bigger. But what it doesn't include is the fire suppression. So thank you to the firefighters who were able to suppress that. Another severe weather application I want to highlight is work done by David John Gagné when he was still a postdoc, using convolutional neural nets to identify probability of hail greater than 25 millimeters. Now, what's novel about this work is not only did he use deep learning, these convolutional neural nets, but he worked to create interpretable deep learning. So the idea is after he applies this to get to the desired label, is it greater than 25 millimeters or not? That was the forward pass. Then he does a back propagation of the error to find out what type of image, what type of input caused that. What do these storms look like? And he was able to identify structures of storms. Here we're looking at two different cases, one on the top, a nice, single mesoscale convective system on the top, and on the bottom we see we have a dipole system, and we see each of those at 500 HPascal, 700, and 850. And this is based on output from NCAR's high resolution ensemble that we used to run regularly. And we'll see that both of these types of storms are really plausible, where we have the types of shear, wind direction, confluence of warm air near the surface, strong lapse rates aloft, and then here grapple seeding at 500 HPascal. We see this complicated structure really is similar to the feeder-seeder mechanism identified by Heimsfeld back in 1980. So we can get some physics out of this and interpret what's happening on these storms that produce large hail. And the impact of this is, first of all, the convolutional neural net had a more skilled hail prediction than other ways of doing it, also encoded the realistic storm features and processes for hail growth, which allows internal representations, can enable more sophisticated analysis of data like this. So this is where we can really advance by applying methods like this. One other method that really catches me, a lot of what we have looked at so far is doing point predictions, and then updates from data at a point. But some work that Will Chapman did when he was still a grad student at UC San Diego with his advisors, he's now a postdoc at NCAR, but he was predicting atmospheric rivers and seeing whether he can improve on, at that time it was still called GFS, integrated vapor transport forecasts. What he used for training data on truth data was the MERA2 reanalysis data. So what he was trying to do is train the changes from the GFS to the MERA using his convolutional neural net for atmospheric rivers. So you'll see that we got this atmospheric river in GFS, but it's not quite in the right place. And what I'm really taken by is the plots on the right, where if you look at the middle one and you see the difference between the GFS and MERA2, you'll see, oh gee, there was a phase shift. GFS had the right structure, not quite the right timing and propagating that. But in looking at the difference with his convolutional neural net from actual, you'll see that he was able to capture that phase shift. And instead of applying just a correction factor, he shifted the whole phase, really allowing an advance that isn't capable using most other methods. I promised to say something about parameterizations. One thing we're working on here at NCAR is surface layer parameterizations. Now, of course, what we typically use is Mononubikov similarity theory, where we set up relationship between variables, and then we have to fit constants using data. And typically, those constants have been fit using data from flat grasslands. Well, that isn't really representative of the world. And since we're fitting constants anyhow, why not use machine learning and see if we can get something other than that rational relationship? So we got two data sets, one from Cabot in the Netherlands, where they've had long-term flux data and a Met tower, and the second from the FDR tower in Idaho, where we had multiple years of data. We fit both random forests and artificial neural nets for both of these. And here's some tables of results. On the top is Idaho. We're looking at two different variables, correlation coefficient, R squared, and mean absolute error for three different variables: friction velocity, temperature scale, moisture scale. Those are the ones that go into predicting the fluxes. Top row is Mononubikov. The second row is the random forest trained at that site. So the top table, we see Idaho. And when we look at that, we see that in all cases, the random forest, similar table for the neural net, we were able to beat Mononubikov similarity theory applied to that site. Same is true on the Cabot data set. But what really is interesting, when we look at the final line in the tables, the random forest trained on the Cabot data applied to the Idaho data set is still better than Mononubikov, and similarly for Cabot. So the conclusion of this is both the random forest and the neural net significantly outperformed Mononubikov theory. And that's true even when applied to a site different from the one it was trained on. Okay, so we did that for a couple cases, but when we look at it, 3/4 of the Earth is covered with water. So what about over water? Can we do that? And as part of one of the projects I lead, and especially using some methods developed by Branko Kosovic with Sue Detling, Tom Brummett, and David John Gagnier doing the work, we grabbed some flux data from the Pheno Tower in the ocean off the coast of Europe to estimate friction velocity, temperature scale directly, and then trained random forests and neural nets again, and found that indeed we still outperform Mononubikov theory even for the offshore environment. Okay, so we developed a surface layer model. Next step is to put it into models. we've done that in WRF. David John is working on that, but we've also done it in FastEddy, a paper led by Domingo Manos-Asperov, working with other machine learning scientists, and as well as large eddy simulation modelers. We applied it in FastEddy. Here on the top right, we see that the turbulence patterns are very similar in neural net as well as Monod-Bubikov surface layer. We also see that the PDF is very similar for the friction velocity, and I'm sorry, this is the friction velocity you're seeing on the top. And then when we look at profiles of the U wind speed over a diurnal cycle, again, we're able to use this machine learning model to get a plausible behavior. Okay, I promised we'd say something about dynamics, and there was a paper by Peter Dubin and Peter Bauer of ECMWF a few years ago. Many of you are probably aware of it. Maybe one of them has spoken. Peter Dubin gave a really great plenary at the NOAA's AI workshop a few weeks ago, and talked about digital twins. What they did for this paper is they made global weather forecasts using a toy neural net model. They compared it to a T21 atmospheric model, similar grid spacing and similar complexity for short lead times. And they found that they're able to do better than persistence and about as well as this dynamical model. So, I think that really showed the community, okay, maybe it is the future as we're increasing computer power. That's a little reminiscent of a little toy problem I did back in the early 2000s, where I looked at the Lorenz equation, of course, quadratically nonlinear model. The training data here is on the top left. I first applied a linear inverse model, and we ended up getting a decaying spiral behavior with a linear model, as one would expect one has to. But if you solve it with a genetic algorithm, pose it as an optimization problem, you can pose almost anything as an optimization problem, you see that you do get this nonlinear behavior, not exactly reproducing. We don't expect it to because it's a chaotic system. And we're in the right areas of phase space. Again, leading to the assumption maybe we can capture some dynamics with machine learning. The one that I'd like to highlight is some work by Dale Duran's team at University of Washington, working with a grad student, Jonathan Wayne, and some colleagues from Microsoft. They built deep learning based convolutional neural network for subseasonal to seasonal forecasting. I'm showing results from their second paper here. It's really interesting to see. It only takes 3 minutes to produce a 320 member 6-week ensemble forecast, and it gets similar skills for CRPS and RPSS for both 6-week forecast and the 5 to 6 week forecast as ECMWF S2S ensembles. Pretty impressive for some initial work. They're continuing their work along this line. Now, at NCAR, we haven't been quite doing the dynamical core, but we have been looking at what happens if we don't have the computer power to do really complex simulations. Can we get that from course data by training doing some deep learning? So first I'm showing you the training data. This is a 30-meter simulation of flow around Mount Hood in the Pacific Northwest. You see the complex flow, meandering wake, gravity waves. Some of them are standing waves, some are shedding. There's cold pools, very complex flow. This challenge simulation took several weeks on about 8,600 processors of Cheyenne. NCAR supercomputer. Now, the question is, can we do something to get that type of resolution with more reasonable type models? So given, we're going to start with 960 meter, roughly a kilometer, and then see whether we can train to that 30 meter resolution. That's a 32 times downscale. And we found it works better by doing it in 2 steps, first a 4 times downscale to 240 meters, and then the 8 times downscale to 30 meters, using a generative adversarial network, which is basically 2 neural networks that work in an adversarial type process. And we'll find that we do get behavior, the fine scale structure in the flow, very similar to the truth data that it was trained on. And you can take from any areas of this original flow, this is the U velocity, and downscale it, and you can see this detailed structure. This happens in all 3 variables, U, V, W, where the coarsened, what it was given, the roughly 1 kilometer, the generative adversarial network in the middle compared to the original data. I was surprised that we could get that close, to be honest. We can do the full domain and on the order of a second be able to do a downscale where it's almost indistinguishable which is which. Okay, what about in terms of variables? Are we capturing that turbulence? And indeed, when you plot the energy spectra, as well as, we've done some validation on some other statistical variables too, we see the spectra is pretty similar, except for this little spike right where we went from the 4 times to the 8 times. We can get rid of that by training the 8 times model and the 4 times model, but we lose a little bit of energy. Now, of course, the real test is, can we do transfer learning? Can we apply the model to something it wasn't trained on? And in this case, we trained the model on the eastern part of the domain, and we're getting these good results because of the underlying forcing. But at the western side of the domain, we have substantially different types of terrain in terms of ruggedness. So can we take the model and apply it to data where it wasn't trained? Okay, input to the model on the left, the result of the generative adversarial network in the middle, and the WRF results here on the right. Again, it's not perfect, but pretty good representation of the detail given that. Again, spectra plots lose a little bit of energy in the transfer region, but still a lot better than we were expecting originally. Now, I want to finish by talking a little bit about where we're going. I started talking about a paper I wrote with colleagues from the AMS. Now I want to talk a little bit about a paper, another group paper that came out of a workshop held at Oxford in the fall of 2019 when we were still meeting in person. And that was organized by Tim Palmer, had experts from around the world. I was honored to be asked to lead a group discussion on post-processing in our breakout groups, and had a really great group of people to work with. And we asked, what is needed to move forward to enhance post-processing? Okay, one is trustworthiness. Everybody needs to be able to trust the AI output, or they aren't going to use it. We can't convince our forecasters to make an AI forecast if they don't trust it. So we have to work in that. To get that trust, one thing we have to do is make progress on this interpretability. Does it make sense? Are we getting the right answers for the right reasons? Data usability. We need to be able to have good data, both to train and to initialize. It has to be in forms where it's curated well and easy to use. And technique. We need to be able to work on technique to advance the methods using this data and using the best possible things out there. How do we know when we succeed? We decided, well, when major centers fully include the AI post-processing as a step in how they make their forecasts. Now, I know some of that work is ongoing at NOAA as well as ECMWF and all the other big centers in the world, but one thing is when the system changes and we're doing an evaluation on whether it's better, are we including the post-processed results in making our determination on whether the whole system has improved? Is it perhaps better to freeze the system for longer, the NWP system for longer, so we can work harder on the AI methods to improve the final forecast in the end? Consider it as a whole system rather than just a post-processor. We need to prioritize computational space and time for developing and applying the AI method. We might want to consider regime-dependent corrections. I showed you one example that we've done. There's lots of people studying regime-dependent corrections. And also, maybe we can run coarser runs that use the AI to get the finer results. I showed you some of the initial good results of applying some of these downscaling methods using deep learning. We came up with a roadmap of some actionable items. One is develop a data repository so that people can test methods and intercompare. We have to have, common assessment and metrics to do that using fair data standards. I think everybody's aware of that: findable, accessible, interoperable, reusable. As we curate our data, studies on interpretability methods. Many of you are aware of Amy McGovern's Center for AI in Environmental Science based out of University of Oklahoma. This is one thing they're really emphasizing. They're making lots of fast progress on that. She could certainly give one of these seminars and make a, disclose a lot of what's happening there. Having metadata as well as your data and documenting the models for our labeled training data so it's understandable and more usable. And finally, a database of recorded AI failures. Not only publish the successes, but save everybody a lot of time by publishing the failures as well. Now, we decided to put our money where our mouth is by developing a first set of data repository. You can find it on this NHAR GitHub. I have to credit Will Chapman with doing a lot of the curation of this data. The MJO and PNA ensemble forecast data was contributed by Anish Subramanian. Will contributed his integrated water vapor transport data that I showed, the atmospheric river results. There's ECMWF 2-meter temperature ensemble data over Germany that's been worked with by Sebastian Lurch. And UK surface road conditions contributed by Charlie Kirkwood. So these are very disparate type of data sets. You can go in there, get the data. We have a Python notebook so you can assess and compare to really basic methods and see whether your method is as good as a basic method or better than others. And if you get great results, please contact myself or Will, and we'd love to work with you to advance. So in summary, machine learning is becoming a necessary component of modern weather forecasting. We have various levels of application. The holy grail is the dynamic core. We're not there yet, and it's going to take a while to get there, but some great first steps are being taken. Parameterizations in models. Some of them are becoming a lot faster. Some of them are becoming better. A way to really better leverage our computing environment. And the low-hanging fruit, post-processing. Model improvements based on observations and post-processing. So what we wish to propagate is this AI physics blended system so that we end up advancing applications of weather forecasting through the systems approach by blending the NWP, the observations, and the machine learning. So thank you. I'm willing to take questions now.
Thank you so much for that useful information. It's very interesting. You do have a few questions. If you can pull up the questions doc, you can feel free to read them and answer them.
Okay, great. I see the first question for Analog Ensemble approach. What are you using to select past forecast? Is it an ensemble forecast? And if not, do you consider the first moment only or second moment? Okay, great question. And how do you treat variables that are not Gaussian, such as Precip? A really good question. So, of course, the devil is in the details, as always. And, how do you find those? You basically decide, it depends on what you're trying to forecast. For instance, for wind, we may be looking at, for wind at, say, hub height, if we're doing renewable energy forecasts, of course, that's going to be one of the variables, but we also have a vector of other variables. We might, for instance, want to glean some stability information and get temperature at a couple different levels, wind speed at a couple different levels. Pressure is often a good variable for things like wind speed. It really does depend. Typically look at, the mean of the prior forecasts. I'm not aware of Stefano and Luca, looking at bigger PDFs. Not usually, it's a very high resolution simulation that they're basing it off of, and it tends to work very well. I can't talk a lot to probability of Precip for analog. I believe they have worked on it. They've also looked at combining several different sites that are nearby. There's various ways to do that. There's a whole host of papers on the way they've applied Analog Ensemble. I realize there's been some great work at NOAA when Tom Hamill was still at NOAA looking at a different type of Analog Ensemble where he really was creating ensembles in a different way. Please, catch up on that literature. If you email me, I'll be glad to send you a list of papers to look at, or email Stefano as well at NCAR, or Luca, who is now at UC San Diego. Analog ensembles need a large historical forecast. And, so again, we tend to like to have at least a year's worth of data. More is better. Having reforecasts is essential when things change in the model, because we do have to retrain models. That's one reason I'm advocating that as we update our models, it might be better to update them less often, but then allow the machine learning models to work on the back end of those so that we're assessing the post-processed results instead of only the results of the NWP. We need to carefully judge machine learning for SDF forecast to compare with the NWP. True, very true. Currently, many statistical dynamic models could beat numerical models. True, there too. And some work that, last year we held an S2S workshop at NCAR, and we had a bunch of bright students and postdocs from around the world there. They all did some projects, and the one I happen to be more aware of is Will Chapman helped with some one on post-processing data to do a better statistical comparison, and found that yes, again, combining the best of the NWP with the post-processing and historical data that can make improvements. Now, obviously, there's a lot of empirical models on the SDS side too that have been successful. Back a long, 20 years ago, I used to play with those sorts of things too, and those are all advancing commensurately as well. Okay, I see another question. How much has ML AI made inroads into the characterization and prediction of geophysical turbulence? Another great question. I would claim that the downscaling method that I showed is going in that direction, where given that we have the underlying forcing at 1 kilometer, and we're able to train this deep learning model to get to a 30-meter structure and able to see the turbulence, able to capture the energy spectra pretty well as I didn't show some of the PDFs and higher moments that we were able to get. I think that's doing a, showing that we can get that in that direction. Now, I'm interpreting yours when you say geophysical turbulence as being fine scale boundary layer turbulence, but I'm not sure if what you really mean is the 2D geophysical turbulence, where we're trying to capture, the coarser structures, perhaps at higher levels, in what may be a more barotropic flow. Again, by applying things such as, what Del Duran's group has been doing, they are able to get very plausible type patterns. So I think we're making steps in that direction, but we're still pretty early in the research. And finally, I think this is probably the last question we have time for being typed now. Are AI sensitive to model resolution or observation density? And that's another great question. The answer is yes. You have to, an AI method can only be as good as its training data. So for instance, when we did that downscaling, we created a machine learning model that can take data at roughly 1 kilometer and downscale it to 30 meters. But that's because we had training data of a large eddy simulation at 30 meters. So, if we could, if we had 10-meter data, could we go down further? Probably, perhaps by using one more step. But if we didn't have that training data, we wouldn't be able to do it. When we're doing corrections, they are only as good, again, as the training data and the observations that are coming in. When we apply diecast, we like to do something that that is more like a, if the obs data don't arrive, we still make a forecast, but we have to make some underlying assumptions, usually around persistence or that our statcast is getting any changes correct. But the models are only as good as the data that go into it. Stacy, so how hard is our cutoff? We're still getting a few questions coming in.
So I see, and we are 3 minutes over schedule. So what we can do is you can answer the questions and they will be made available to everybody if you can type them, if you don't mind.
Sure.
Okay.
One more that I just saw got typed, I really want to say something about, is incorporating physics into the loss functions. Great question again. That recent work, you are aware of some great recent work that's happening. It's also happening, in the environmental community, hydrology. They're, putting boundary conditions and physics in it. And to be honest, when you go back to what we used to do in genetic algorithms, we basically put the physics in our cost functions. And that's been ongoing. I showed that very simple example of using a dispersion model to try to correct to get the right indirection, the wind direction, and the dispersion model, knowing the physics of dispersion, including some information about stability, etc., was part of the cost function. So we were estimating what the dispersion model said, comparing it to the measurements in the field, and trying to minimize the difference by calculating a better wind direction. And it worked. I expect that many of the other methods will be going in that direction in the near future. There's some work on that being done at Colorado State right now. And again, there's some great work going on around the country and the world. So thank you for asking that question as well. So I'll be quiet now, Stacy, and let you end this.
Thank you so much. It's so much information. It's a lot. It was a great presentation. So yes, this will be made available to you and to everybody. So if you feel free to answer the questions that you have not, or go more into detail, and you can get them back to me. I have access to that all times. Thank you very much, Sue. This was really great, very informative. As you see, we went over. So I appreciate you, and thank you, everybody. We will be reconvening next month. Have a wonderful rest of the day.
Thanks for inviting me.
Absolutely, you're welcome. Thanks, everyone.